could be because Taurus GUI is blocked waiting for that response, or it could be because it's not getting any updates. If we send the I don't know. Plot options. Okay, there's a change. Apply. No. Does apply. Okay. No. No, I can't change it. Okay, you can see something there.
Would you probably just dim the light? I will ask to dim the light. Continue.
Okay, so I use a different client from Jive. I send this command. You can see that the graph stops. But then you see it zooms really fast after that. So that's because we have this background process that's putting the samples into the queue. When we try to push change event, it has to get the monitor lock to push the change events, but the monitor lock is taken because we're busy with the average stats command. So it's just queuing up that data, and then at the end, when it gets a chance, it sends through the old data. If I make this time more than 3 seconds, you'll see in the logs here something about the Tango monitor. Let's close this. As you saw a timeout from Jive because the client didn't get a response in 3 seconds. So Jive gave us an error. And then we also had this exception, failed to push change event for CPU percent. They failed, and I'm sure a lot of you have seen this method, this error that's hard to diagnose. Thread 6 not able to acquire serialization monitor held by thread 7. So in this case, we know that thread 7 was the thread that was handling that command that was running for 4 seconds. And thread 6 is the one that's trying to publish the events. So it gets blocked. It tries to get the monitor lock. There's a 3.7 second timeout on the monitor lock. If you can't get it, you get this error. Okay, so that's a slow command. What can we do about it? So one way to solve it is to change things dramatically. And let me hide this. I'll show you that code. So we make average stats non-blocking. And what's going to happen here, let me just maybe run it first. I'll run Taurus again. Okay. So now what I've done is I've changed the average stats command to be called start average stats. So it's just going to request that this work runs, and it's going to run in the background. And when it's finished, we're going to see the result in a new attribute called average stats result. So now I can do this plot again. Speed up the sampling rate. Okay, sorry, it's hard to read. So if we do average stats, we can do 10 seconds. You'll see nothing happens on the graph. In the status, it says average stats is running for 10 seconds. And now it's changed to average stats completed for 10 seconds. And if we look at this attribute, average stats result, here it's got the long JSON string with our result in it. So now we've changed the API quite significantly. We've also got a command called cancel average stats. So we can interrupt that method. So you can apply this kind of pattern. But there's a lot of infrastructure you have to build into the Tango device to do it. SKA have got this base device and they've implemented a whole mechanism for long-running commands in there. So let's have a look at some of the code. So first we look at the data access layer. And here we've added a new exception. And when you call this average over method, you pass in a threading event because we want a way to cancel it. So we need to pass in some event that we can trigger from a different thread. So now while it's in that loop doing this, the averaging, if it sees this cancel event is set, then it can abort early on. Then if we look inside the device code, again, a lot of things had to change. We import this error. Now we've taken that old event queue, which had the samples in it, and we've renamed it to sample event queue because we're going to add a second queue. The second queue, I want to handle that new attribute that has the result in. So when this job is finished running, I want to push an event for this average result. And I don't want that to go into the sample event queue because it's not really a sample. And also, it's more important than the sample events getting to the client. If they started the job, we want them to be informed when it's complete. We don't want to drop this sample. You remember that this event queue was bounded, and if it gets too full, it'll start to drop things. So we've got a second queue. Then we've got a threading lock to help us. We've got a structure where we can keep the details of the job that's running. When we delete the device, we have to cancel the job in case it was running. In dev status, we're adding an extra line of text, which is telling us what's the job busy doing. Is it finished? Is it canceled? Was there an error? And okay, sample rate, we're going to, previously it was just using this push paired event, which was pushing change event and pushing archive event directly. Now, because we have this new queue, I've just put it in there as well. Okay, new command, new attribute. This is the average stats result. So here it uses that lock. It looks at the job, it gets the result of the job, and then returns it. And the timestamp it's going to use is going to be the timestamp that the job finished. So we use this tuple with 3 values so that we can return the timestamp. And then our old average stats command, we renamed to start average stats because it's not actually doing the work, it's just scheduling the work. And now I can go to the full code. So there's a lot of boilerplate you have to do. You need to have this cancel event, you have to take the lock, you have to make a new thread. So this new thread is going to run, wait for the actual work to complete. We've got this class that keeps the details of what the job is doing. And finally, we can start our thread, and we return a message to the caller saying, yes, it's running. We've got a command to cancel. So again, we just call a method to do that. Let's get into publishing. Okay. So publishing is interesting now. I said there's 2 queues that we want to publish from. And in this example, the one with the attributes in is considered high priority. So this loop is going to first try and publish something from the attribute queue. If it does, it's going to continue and it's going to keep going until it empties this queue. So the attribute events have higher priority. Once we've published all the attribute events, we don't expect there to be very many, then we can go back to publishing the sample events. So that's another small change we had to make. Yeah, I think that's the main details I want to show you for this. So it's complicated. to handle a long-running command like this, you need a lot of infrastructure. And if you have more than one task running, you've got to do something else. So it can be very complicated. Okay. So then I wanted to move on to green modes, because that's again another way of dealing with this. So if we go to the Pytango documentation, under tutorial, green modes, we've got client green modes, which would be if you want your device proxy or attribute proxy to behave in a green mode way, like async IO version of the device proxy. But I'm interested in the server green modes. So here there's two options, gevent and async IO, and then the default is synchronous, which you don't have to choose. So we're going to use async IO. There's a warning here, and the warning says that when you use one of these two green modes, we disable Tango's device server serialization. So there's a thing called the serial model, and we set that to no sync. And if you do that, it means that when you're handling a read attribute call or a command, with the synchronous mode, only one of those things can happen at a time. You have two clients who both request a command, it's going to service one completely, and when it's finished serving the first client, it's going to start the command that the second client asked. If you turn off this synchronization, or you turn on no sync, then when those two commands come in, your device server can actually run them almost in parallel, depending on the threading model you have. So then you've got to make sure that your handlers are safe to run sort of concurrently or overlapped. So you have to be more careful of how you write your device and how you write your handlers. So async IO makes it a little bit easier because it's cooperative. You have to use await when you want to give up control. So the important things in async IO device is to have set this green mode attribute to async IO, and then all of your methods will change to coroutines. So you need to have async in front of the name, and then for init device, if you call this superclass method, you have to await it. Your commands become async, so now you're allowed to do async things inside those commands. So let's have a look at. Okay, in the repo, what I did is I first took a copy of the synchronous device, and I copied that to device AIO, and then I made another commit where I modify that synchronous one to async IO. So we can see a diff, what changed to switch from sync to async. This one is called the async resource reporter. We set the green mode, we change things to coroutines. Our queue is no longer a normal queue, it's now async IO queue. Instead of a publisher thread, we have a publisher task. Oh yes, we also have an async IO version of this data access layer. There we've changed things to coroutines and we're using tasks instead of threads. So you need to have that as well. Yeah, delete device, we await stop, we await when we delete the device. So these are all pretty simple changes. And when we do the publishing, again, we're using async IO methods for doing things instead of standard threads. But the code looks almost the same. We don't need this ensure omni-thread anymore because the task that's going to be publishing our events is going to be running in the async IO event loop that Pytango created, and that one is already omni-thread. So we don't need it. But sometimes if you're using an async IO library, it might start its own event loop in the background. That thread that it's running in is not an omni-thread. And then when you get callbacks from it, then you have a bit of trouble because they're coming from a different thread that's not an omni-thread. Then you might have to put that into a queue or do some synchronization. can be tricky. Okay, so let's run this one. So this is Money async DS. Oh, can't run it. It's a pity. I haven't checked it out yet. Okay. All right, so now we're going to use two clients. One will be Taurus. Sorry. Okay, so the Tango device name we're using is now ARR. Later on, we're going to run both of them, so they've got different names. Okay, so we're pushing events. We are going to call this average stats. Yeah, wrong device. Let me do it the other way. So I'm going to call it on this side. And then I'm going to be able to read state. And so you can see while Taurus is running average stats, the graph blocks, but I can still execute commands with a second client. So if you have two different clients talking to this device now, then one of them is going to be blocked when it runs a slow command like average stats. It can't do anything else, but other clients are able to read attributes or send other commands. So this solves one of the problems where you aren't blocking other clients, but it's not as good as the previous example where you actually run the whole command in the background, because then even the first client can do other things while it's waiting for the work to continue. But it might be good enough for your problem, so yeah, that's an alternate solution. Okay, next thing to show you is the state and status events. What if you want to push state and status events? Up to now, we've only been pushing the events that have the CPU and the memory usage and the disk usage. We haven't pushed state and status. And that's also quite complicated. So at the bottom, what we need to do is we need to say push change event and push archive event. Normally, you would give a value, a timestamp, and a quality when you call the push change event method. But CPP Tango will ignore those things if you pass it for state and status. And it will call self.getState and self.getStatus, and it will use that value instead. That's what it's going to publish. It's going to use the current timestamp, and it's going to use the @valid. So we need a special way of pushing those events. We can't use this. We had a paired. Yeah, sorry, let me go to the code. Let me show you diff. All right, now we go back to init device. So here we've added two things. We want to override the event snapshot and the event snapshot history. You'll see why just now. We call set state, and now we're going to call set status because we can no longer use this internal automatic status that CPP Tango does for us. I'll explain why a bit later. Okay, sorry. When we are reading attributes, we use this snapshot, and now we're going to have a way to override the snapshot, because when we get an event, there's all these sample readings, we want to calculate state based on those readings. We want to push the state and the status based on those readings rather than the current readings. They should be almost the same because we're publishing really fast, but to be safe, you should recompute state based on the readings that just came in. And you saw earlier when you call dev state, it will, TPP Tango will call the read attribute methods for all of the attributes that have thresholds set. So we want a way to make those read attribute methods return something different, basically the snapshot data rather than what the monitor currently has. So that's a complication. Right, when we publish sample events, these have now become coroutines because when we are calculating the state and status, we need to execute dev status, and we need to await dev status. Sorry, no, this is quite complicated. All right, so push state and status. It will first take the current snapshot data, or current event data. It's going to set the overrides. Then it's going to call dev status, which is going to get TPP Tango to reevaluate the state. It's going to read the attributes it needs to. They're going to see this override value. And finally, when we're finished, we can clear those snapshots. So you should just be doing await self.status here. But the way I implemented the test, it doesn't need to be awaited because it's using a different async IO loop. So we have this special check for is awaitable. Finally, we have, when we called dev status, it's set state and set status. So now we can push these built-in events, and they're going to push those values we just computed. So it's pretty complicated. This is because we are using this built-in state. It's just checking the alarm thresholds. If you don't care about that stuff, you can do this in a much simpler way. You don't have to read the attributes to compute states. Okay. There's an example of doing this in the synchronous device as well. And the only thing I want to show you there is when you're doing recalculating state like that. Right, so we have this push state and status. There's a hidden feature in PyTango called Auto Tango Monitor. There's an issue to document it, but we haven't yet. But if you use this context handler, what's going to happen is you're going to take the monitor lock, which means that no other commands or attributes can be read while you're busy. And we're taking that here because we want to recalculate status, and we're going to set these overrides, so we don't want any external clients to see the wrong value while we're busy. So we take this lock, we modify it, set our override, do the calculation, replace or clear the overrides. And then we're going to do push state and status events. And we can do that while we have this AutoTango monitor lock, because you need the lock to push events anyway. So we might as well push them before we release the lock. Okay, more tricks. Then a new feature which is in CPP Tango, also in PyTango 10.3, is called PyTango thread. And what that means is you don't need to use ensure omni thread anymore. So if we change from a standard thread to a PyTango thread, then this code, which is the main loop, it can just be normal, and we don't have to have this context handler. So if you're using a target for your thread, or if you're inheriting and overriding the run method, this works for both cases. So this was a nice addition that we've got in 10.3. Time? Okay. Approximately. Okay. All right, so then I wanted to show you if we add another device into the hierarchy. So we mentioned the facade device or the pattern of facades, and there's a library called facade device, which was written by someone at Max4 a few years ago. We use this for a lot of our PLCs. A PLC has got like 100 tags, but it's many different subsystems are actually read by that PLC. And then we use a facade device to sort of take a few of those tags and make another Tango device that just represents one vacuum gauge or one temperature sensor or something like that. So the facade device is a nice library for doing that. It's async IO implementation. In this case, I'm going to add two attributes, average CPU percent and average memory percent. And you can then tell it to subscribe to attributes on other Tango devices. And as the events come in from those external devices, it gives you a callback. So in this case, we're just going to average all the values we have, and that's going to be the value we see on these two attributes. There's also a nice presentation from Eclipse in Barcelona in 2017. So if you want to read about the reactive programming model that's in this device, have a look there. Okay, so we had a start averager. So now I'm running all three device servers, a synchronous version, async version, and this averager device. We can oh, it's in fault. Probably started too soon. So I try to subscribe to the attributes at startup. If the other device servers weren't running yet, it might fail. Okay, looks better. So you can see these two new attributes, and they're updating as the events come in on one of the other devices. So if we speed up one of these, we change sample rate. Right, so now you can see the events are coming a little bit faster, and this device is reacting immediately and showing us those values. The code is very simple. So there's facade device. Basically, you import facade from this library. You inherit from it. You can do something in init if you want to. And then there's a couple of new decorators like combined attribute. So it's a float. This is the property it's going to look in. So inside this property, there are a couple of wildcards which say which attributes to subscribe to. And then it's going to call this function with a number of args equal to the number of attributes it's subscribed to. And it's going to give you the latest values for all of those arguments. So we're just calculating the average. So there's a lot of nice features in this Tango device. Okay, I think we're done. So any questions on this? And I've gone very quick.
Yeah, okay. Thank you, Anton, for this example of extremely simple PyTango device. I think 99% of PyTango devices developed in Daisy are simpler. But now, time for questions. It's just a joke, Anton,
No.
But it was really very impressive. Questions? Yes.
Yeah, thanks, Anton. The push change event acquires the monitor lock. So if I have my queue being filled up very quickly, and each time I call push change event, that is taking, I don't know, is it a second or two, it means that so long as the monitor lock is being acquired if a client tries to read my device. That'll block it, right? So in your example, I saw you were increasing the frequency that I think
The sample rate.
Yeah, the sample rate. But your client, your device was quite responsive. You could still read. So the question is, are you draining the queue at a certain cadence?
No, I'm taking one item at a time. So you could take more if you want, but it's the pushing events is really, really fast. It just gives the data to 0MQ and it sends it. It's very efficient. The problem is if you're busy handling a command or read attribute and the monitor lock is not available, then it takes a long time. But normally it's super efficient to push events.
Right.
So it shouldn't delay you. I think Sergey was talking about a device server they have which gets data in chunks, like it gets 1,000 bits of data, and then it wants to push all of them. And they actually decided to push that slower because the clients that receive all the events can't deal with the events coming so fast. So they artificially slow down how fast they publish to help the clients who are receiving the events. So it's pushing the events is not normally a bottleneck.
Right. Okay. I mean, even with the example you gave, if my events was not coming in like in a huge chunk, but it was just coming. It's a single event, but it's coming in very fast. So I mean, it's quite a lot you're processing at a time. It means that if a client tries to run a command, which will acquire the lock, then you could have a deadlock. You can have a.
It should get a chance, right?
Right.
I mean, there's OmniOp or CPP Tango is processing a list of requests. So it's got some push events there, somewhere in that a request is going to come in from a client, that's going to be scheduled, and it's going to get a turn. So it should get a turn in between. It shouldn't block the external client, unless the load is so high that it just can't keep up with all the requests.
Right. Okay, thanks.
Okay.
Thanks for the demo. It was great. I just want to relay a question from one of our developers who's just ported a device from using async IO to sync in order to upgrade to Pytango 10.3. So, yeah, Rodrigo said synchronous servers are clearly more mature, and I feel like with our async IO device, we were always a bit of a guinea pig. So maybe a question to the community is, how widely used is this mode in other Tango projects, and are other users facing similar issues? So do you agree with the characterization to begin with?
Yeah, I think async IO is the least mature of the device servers. Synchronous is definitely the most solid. And yeah, people have been guinea pigs. We've fixed a lot of issues with async IO, but I think there's still some more. And most of it comes down to this no sync serialization mode, because now you're taking away one of the main locks inside CPP Tango, and that can cause problems. We've got plans for CPP Tango 11 to kind of separate publishing of events and reading of attributes a bit more, but currently they kind of share data, and so there has to be a lock around that, and when we take away this lock, then we see crashes and we see problems. So it's getting better, but yeah, I would do synchronous first.
Thanks. And in terms of adoption, like do you know, or could we maybe have a show of hands in the room or something to see who's implementing these?
So Max 4 is doing a lot of them, at least for this Averager, this facade device, and they are solid. But we don't, the way we use them, I guess, is quite simple. So maybe async IO, who's using async IO green mode devices successfully? Okay. Yeah, it's harder. And TI?
Just wanted to comment about this because there's an historical reason why the default model in Tango device is serialization. Is that in the original design, the Tango device object was supposed to be the gateway in front of your hardware. So most of the times, it was the proper design to serialize all the requests in order to serialize the request to the hardware. It's clearly a model nowadays is a short cover. So, but still there are devices, lower level devices, wherever you have this on top of other kind of slow hardware also, which will benefit from serialization.
Yeah. Okay, we do.
So I think one of the main issues with the no sync mode in CPP Tango is that we share the same slot of memory for pushing events and for reading attributes. And in the sync mode, we use the device serialization to ensure that there aren't, so to protect that piece of memory. So if you're pushing an event at the same time as and the client is reading, then that's guarded by this lock. And if you go into no sync mode, I'm starting to realize this is something I've only sort of recently become aware of, but we're essentially pushing that responsibility onto our users. They have to ensure that if a client is reading that attribute, they are not concurrently pushing an event at the same time. And we probably need to document that better, and we probably need to avoid that. Like, that shouldn't be the case. But right now, that's, I think, what a lot of the problems that people run into is that they haven't realized that because we've not really told them.
But the Python layer, you can't prevent it, right?
Isn't that a bug in 9.3.4 that was fixed in 9.3.5?
It's not really ever been fixed properly. And you can have your own locks. You could have like granular locks per attribute or something.
No. There was one problem we couldn't fix from the Pytango
yeah.
side.
Yeah.
Was it ever? Did you ever think about adding a timeout metadata to a command so that in the client side you more or less know how much time you could or should wait? Because this blind 3 seconds sometimes can be a bit annoying.
Yeah. For Tango we haven't. My previous project on the Meerkat telescope, we did do this so that you could have hints, like when you get the API of a device, it kind of gives you the timeout hint that says, okay, you need to wait 10 seconds for me or 60 seconds for me. That would be interesting to add. It would be a really IDL change, I think, attribute config change.
Yes.
And then,
But the question is a static hint in the code really the thing you want? Or
No.
would you more have something like a historically, the last 10 times it took on average?
well, except when you start up the device server, you don't know.
Yeah.
I think could be beneficial.
Okay. Yeah, it had to maintain backward compatibility, of course, and it would be just a hint for the client. He could then do whatever he wanted, override it, I mean. Okay, thanks.
Sorry. We don't have a mic. We don't need a mic. People online can't hear you, Lorenzo.
You need a mic.
Can you pause?
A question: the existing callback model is not enough?
Oh, yeah. So when you send a command, you can send it async. There's a command in_out_async. So if you use that, then you're just sending the request via callbar, and then you check for the result yourself later. You wouldn't know how long to wait before you give up without the hint. But that async mechanism can help you in that case. Yeah, I didn't show that.
Yeah, if I understood correctly, Pytango implements its own event loop. It enhances the async IO event loop and uses, for example, this ensure omni-thread wraps it. What other things does it do?
What other things does it do?
Like key things, yeah? A part of using this ensure omni-thread that you don't need to use. Are there any other key things that this event loop does?
No.
No, it's just basically async event loop, but we just guarantee that it's also ensured on with OmniOrb. But then we are just relying on async library completely.
Yeah. So we have our own thread pool executor version as well that has this ensure omni thread thing. Yeah.
But this is,
Okay. Do we have more time?
no, I think we actually should continue because TB told he needs 20 minutes, and we exactly have this. Okay. Thank you, Anton. And now it's Thomas Brown from Byte Physics Company, and he's going to show, as far as I remember, subscription modes. Yeah, TB. Yes, the new feature, which no.
No? Yes. Okay, now good.
Yeah.
Okay.
So,
Sorry. Yeah. Thanks for the introduction. So I will show the event. So I will show the event subscription modes, and I will show that also with using a C++ device server, just because I am actually a bit faster with writing C++ device servers than Python, because my colleague Michael does currently all the Python device servers, so I wanted to, avoid having to bug him with basic questions. I used, that's a bit large. Okay, is it only large on this monitor, or is it on everyone's Okay. Yes, I have no idea. Well, I can make it smaller, but the question is that really helpful? Oh yeah, okay, so so laptop Bildschirm. It takes, yeah, so I will talk about the event subscription modes. Yeah, okay, now we need bigger again. Okay. Okay, so in CBB Tango 10.1, I added new modes to subscribe to events. That was a project started by Alba, and they contracted us to do that. And the idea, or the problem is that if you subscribe to an event, like before 10.1, you had only two subscription modes. You had the sync read mode and you had the stateless mode. And if you look at the different columns, what they do, you see that they both read the entity. So if you have an attribute and you subscribe with sync read, I mean, it wasn't called sync read back then, but that is the equivalent of the previous method. It always read the attribute, and then it sent you the first the value it read with either with a callback or with the event queue. And if you there was an alternative to use stateless, which had the difference that it didn't throw on a subscription failure. So meaning that if you couldn't subscribe to the attribute, because for example the device server is down, it's still returned, but if it succeeded, it would still read the entity. Yeah. So then the question was, okay, what new modes do we need? And we didn't add all possible modes, because I mean we have like three columns here. You could have said, well, we just do 9 different modes, and it's actually 8. But we didn't do that because it's not really you don't need all combinations. What you want to do is you want to, for example, you want to skip the reading thing. Yeah. So that you just say, okay, well, I just subscribed synchronously, and I got an exception when the device server is down, but I don't want to read the entity. Okay, that's the sync mode. But when you say, well, that you subscribe to the attribute and then return to the caller, well, maybe we can do that asynchronously because it saves time on the client side, because it's the problem is that if you subscribe to a lot of attributes, that takes quite some time, and the client actually is not really interested. In most cases, really interested if it's subscribed after it returns, because usually you either give it a callback or the event queue, and then you can look into that and to see if the subscription was successful or not. So this is the async and the async read modes. Only difference being that in the async we don't read the entity, and in the async read we read it, and for compatibility reasons the stateless property is still there. And so this is added in 10.1, and there was no 10.2, so this is in 10.3, it's still there, yes, of course. And now what I did, I developed a C++ device server where you can play around with these event subscription modes. And it was already mentioned that you should use Pogo for C++, and yes, I also use Pogo for that, because that's what Pogo is designed for. And Pogo is a application, a graphical application where you can, if you're a big fan of mouse use, you can define your device server. And the interface I envisioned for this playing around with the different subscription modes is that you say, hey, I have a bunch of device servers, so and I want to subscribe to a bunch of attributes from these device servers, and then I want to get back the time the subscription took. Yeah, and then I also want to read at the events which were received, because of I need some way of figuring out if things worked or not. And yeah, so that's basically the requirements for the device server. And that means, okay, what do we need? We need a device server attribute. So it's called a spectrum attribute, which is basically like a 1D attribute. So it's an array of strings having a list of all the, well, it's not an array of a list. It's a list of device server. It's a list of strings which hold the device server names we will subscribe to. We have a scalar string attribute which is called received events, and we stringify the event data object we get. We stringify that into a string and write that into the attribute when you query it. Yeah, and then we have 5 different methods called subscribe, sync, read, and so on. And they have, I found this new feature here, which I didn't know. So you can do summarize here, and then you have a list of all the commands you have. And they all accept a def-var string array. So this is an array of strings as input argument, which gives the attributes you're subscribing to, and it returns a double, which is the time in seconds it took to do the subscription. Yeah, so pretty easy interface. I will not show you the code. I mean, I can explain it because I wrote it myself, but it's not very enlightening. It's also this protected region thing in Pogo is also, but yeah, well, you have to get used to that. To write your code in the right place. I mean, it usually tells you where you should write your code, but it's a bit confusing. Okay, so I filled that. So the way Pogo works is that you say, okay, here is my device interface, and then it generates code for you, and you have regions for where humans write code, and you have the region where Pogo writes code, and you always want to ensure that these don't clash. And if you change something in Pogo and regenerate, you usually learn if you respected these rules or not. So I would also always suggest to like commit your changes before you regenerate with Pogo, just to like reduce the swearing. But for C++ device servers, I would still recommend doing that. We have in CDB Tango, Thomas Ives developed something where you don't need Pogo, where you have some kind of like introspection using C++ 11 capabilities, and that would be also a nice approach. But we never made that a separate library, so you would have to like cut that out of CDB Tango and then maintain it yourself, or maybe create that library yourself. Yeah, that would be cool. But if someone jumps at it, yes. But yeah, so for now, Pogo is the best choice for C++ device servers. And just as a hint, I mean, nobody's really jumping at like writing C++ device servers, and that's actually good, because the only reason you should use C++ is if you really need the raw speed. And usually that's not the case. And if you think it's the case, you should really think hard about it again, because it's usually not the case. So just use PyTango and Python, because it's enough and it's easier. Because I mean the memory management for the string stuff you have to do yourself manually, and that's a bit daunting. Yeah, so I wrote that. I got it hopefully working. I would be interested, who is writing or maintaining C++ device servers? Are you using something like address sanitizer and things like that to like ensure that it's really solid? Yes, you're using? Okay. Yeah, okay, because I'm trying to get that for Tango database done as well. And the first thing I found was some issue in CBB Tango. But yeah. So there is still some work to do. But yeah, so I really, if you do C++ device servers, use ASAN, UBSAN, and maybe even TSAN for your own stuff, and ignore the issues. The TSAN issues in CDB Tango. There are no other issues right now, but the TSAN issues are still there. Okay, so with small discretion. Yeah, so this is, I'm using Jive for playing around. And so this is the Moni DS, which Anton showed earlier. And I have this, so this is a test device panel from Jive, which I opened for the event subtest device server. And I also added polling to some MoniDS attributes, because the subscription is done on the change event. And for a subscription or a change event to be successful, the device server either has to have enabled change event, the change event property on the attribute, or you need to do polling to have that called, and then you can send out a change event. And I did, so I just needed there's some configuration to be done if you want to use all these attributes. Otherwise, if you don't, I mean, you can just have a look here to the polling. So you just need to enable polling here for these attributes, and you have to, and you have to either, I'm too fast? Okay. And so in the, in Jive you have these, you can set the absolute and the relative threshold for the change events, and if you do that, this is required. Okay, so what do? We use our device server attribute. So this is a read-write attribute, which we can write the name of the device server. I'm only using one device server because, okay. And now we have it. Okay.
Okay, yes.
Yeah. Okay. So we write the device server name in the device server attribute. We do write here, and it's there. And in the meantime, it's really taking a bit long. Yeah. So. Yes, written. Okay, it took 1 millisecond. The rest was Zoom. Yeah, so we have now set the device server name. Now we need to switch to the command tab, and we enter some. So we enter a list of attributes we want to subscribe to. And for example, we say, hey, well, yeah, let's subscribe to let's subscribe synchronously. We have the battery power plugged, the CPU percent, memory available, and we have a process.json file we subscribe to. So yeah, let's subscribe, and we do that. We press the execute button, and it's done. And it took, yeah, so, and it returns a double, and this is the time the subscription took. And also Jive tells you number, because, but the number Jive tells you is from the client side, and I'm just measuring the time it took subscribing, so that's why the returned value is a bit lower. Well, okay, in this case it's a very tiny bit lower, but usually it's a bit more lower. And so yeah, so it took 200 milliseconds to subscribe to that. If you do that the first time after startup of a device server, you might see that the first call is much slower than all other calls. This is because we only ramp up the whole event system on the first subscription, which is also actually up for debate right now, because this is kind of, it's also a bit tedious in TBB Tango to handle, because we always check, well, is the event system already up, and not we start it up, and it also has the issue that the ports, the TCP ports, the event system uses are not open until the event system is used. So this is a bit, for debugging, that's a bit confusing, because if you want to like do some debugging, you don't know the ports until it's open and so on. Yeah, so that's why this might change in the future. It's also, I think, no problem, because the event system is usually always used for modern devices, so this is not a big deal if we just do that on startup. Okay, so we have used the sync read. It took 210 milliseconds. Let's see what we got. If we change to the attributes tab, we can use the received events, and we do a read here. And you get a lot of data in the read. And so this is a list of yeah, that's good. Okay, good. Okay, so you have we write the demo RR1 device server into our device server attribute, and then yeah, so we have the for example, we have the sync read, and we do the processes JSON, and we do the CPU percent history. Oops, yeah, and we do the sync read. Processes. Oh yeah, that's the thank you. Polling. Okay, so what we need? We need processes JSON. Attribute processes JSON. You checked out, no, here it is. Processes, volume, okay. Yeah, no. Oh, yeah. Well, let's not change too many things. Yeah, so we have a processes JSON here, enabled, and if we processes attribute not found. Processes JSON. What did I processes JSON? What did I change here? Okay, I think it's correctly written here, but processes JSON. Processes. Ah, these are. Yeah. Okay. It's yeah. It's okay. Yeah. Sorry. It's I'm not used to Spanish keyboard layout. It's okay. Yeah. That will actually be better once we do a validation of attribute names. Because you will get a message that, hey, you can't use that character here. Yeah. Okay. So thank you. Yeah. Okay. So we're back to subscribe in sync mode, and it takes around 11 seconds, milliseconds. And if you do sync read, it takes 18 milliseconds, 15, 18. And yeah, and the reason is very simple, because we do less work in sync, because in sync read, we really read the attribute and then only return. And in sync, we don't read the attribute, we just return after we have a successful subscription. And if you say, well, what does async does? Async takes here around 7 milliseconds, and async read. Okay, does async read take longer or shorter than async? Yes, because it's all done asynchronously, so you don't notice. Yeah, so it's basically the same. And if we then read what we got back, we can do that with the read thing here. And yeah, so it's a huge bunch of, it's a stringified array of elements, or it's no events. So I'm using the event queue. I'm not using the callback system, which you normally use for events. But the event queue was just easier for my use case. So where sometimes, and when you read the attribute, I'm just iterating over all subscribed events of all device servers, and I'm just emptying the event queue, and it can happen that the event queue is just empty and then we have no events. And this is, yeah, and now you might wonder, well, why don't you always use async? Well, one thing which async is potentially a bit confusing is that if you say, hey, I'm subscribing to a attribute which doesn't exist, and I call that, or you have a typo in your attribute name like before, yeah. And here I just use an attribute name which doesn't exist, and it's called I don't exist. And if you do an async subscription, yep, done. And you say, yep, top. That's really cool. Yep. You could do that, but actually if you read what the received event says, it has an error stack. Well, because we didn't check that the attribute exists, because that would be the whole goal of the async mode is that we do as little as possible. And the only thing we do, we give the data you give us, we put that into a queue, and we send a message to the thread which handles the subscription to have a try again, because that's the event keep alive thread, and that's not running only for the async only for the async work. So it's also doing other tasks, but we send it a signal to say, hey, here, can you have a try again? And now you have this nice error stack here, because we tried to like subscribe to a non-existing attribute, And in Tango, an error stack is a bunch of exceptions. And every layer which found something then adds something to the error stack. And so you have the first is the utter not found error. And this is then succeeded by the command failed exception. Because the subscribe event, the setMQ event subscription change command failed. And then it's also added the DS failed registering event thing because it failed registering. And this is also not retried because, well, yes, you can think if you have a very dynamic device server, maybe the attribute comes up at some point, but we don't do that right now. So that's just not tried anymore. And if you do, for example, with the same I don't exist name, you do the, well, async read does also work in the same way, but if you do a sync, you get, oops, I don't exist, attribute not found. Yeah, okay, so this is a difference, and you need to be aware of that, but yeah, I think I'm actually done with the event subscription mode changes. Sorry for the technical difficulties. And if you have any questions, I'm happy to try to answer that.
I thought the async modes will retry every 10 seconds. You're saying they don't retry if a non-existent attribute name?
I don't think it doesn't retry. Yeah.
If the device wasn't running?
Yes, that's a different error. That's a different error. If the device is not running, we retry. But if the attribute doesn't exist, I think I haven't really checked the code, but from playing around, it doesn't retry. If that should change, we can change that.
And will stateless still retry regardless or not? Stateless is just...
Stateless is the old approach. We can try. If we do execute, okay, worked. We do received events, we have this arrow, and then we don't have any events anymore.
15 seconds.
Okay. So this is, you can say the bug is preserved, but yeah, if we change, you could, yeah, as I said, with the dynamic devices, you can think about that, okay, an existing attribute should be the same as a non-existing, non-running device server. Yeah, that could change. There's also a request that right now the device server has to be exported in a database, so the Tango control system needs to know about the device server for you to be able to subscribe. That's just a technical limitation because you need a proxy object. You can also imagine that the device server doesn't need to be exported because actually, if it will be exported at some point, that would also be enough. But that's just like because of how we do things, but we can also change that.
Okay, thanks, Thomas. We are quite short of time, so if nobody has a very fast question, we proceed with Thomas Ives' presentation. Now, you want to present Thomas? Yuri?
Yeah. Okay. So this is Thomas Ives from Observer Science company, also one of our partners. Tango Collaboration is going to present events system monitor he developed and added to the code in 10.1. Yes, 10.1 new feature.
Hello, can you hear me?
No?
Hello? Okay. Good. Is that big enough? Can I make that bigger? Okay. Yeah, so I'm going to talk about this query event system thing that I've added to Tango 10.1. And so I've got Yuri's device with the averager running, so we can have Anton's averager device running. So we can have a little look at what the event system is doing for this device because it subscribes to something else. So I'm going to just, in Pixie, start iTango here, and hopefully, Pixie exec iTango is what I need. No. I don't install anything. Okay, so yeah, so we can get a device proxy to that demo AVG1 device, and we need, so this is a device proxy to that device itself, but this query event system command is on the admin device, so we need to go grab that, and you can use the ADM name to get the admin device name, so we'll do this. And then on this admin device, there's now this query event system command that we can call, and we get an awful lot of JSON, which maybe if I import JSON, and then we could do, I think I've done this before, yeah, we could like pretty print it a bit, but there's quite a lot of information here. But this is essentially just a dump of some internal data structures inside CPP Tango about what's going on with the event system, because it's there for debugging things, so we don't really know what information to report. We're just reporting all the stuff that's there. What's kind of interesting to show at this point is there's this path here that's null, and this is because we don't have performance sampling enabled. And we can do that by calling another command called enable event system perfmon, which is a terrible name, I'm sorry. But we can go and call this again, and if hopefully some events have happened, wrong one. Query event system again, and I should probably print it so we can see some stuff. And here we've received some events, and we get some information about how many microseconds it took to process this event, what was the latency. So this here is surprisingly large. I don't know if this is something. This is how long it took from when the server sent the event to how long it took until it started being processed by a user callback. As this here is 100 milliseconds or 140 milliseconds, which seems quite long to me, but maybe my computer's slow today, I don't know. And we can see similar things, like if we pushed any events on the server side, we get some similar sort of data here. But all of this is quite hard to follow what's going on, and really you want to be sort of seeing this over time. So at SKA we've got some script called SKA Tango Monitor, SKA Tango Event Monitor, sorry, which will try and, which here's the documentation for it, and it'll take snapshots of these big JSON dumps, and then it shows you the difference over time, so you can kind of see what's going on in your event system, because often it's the differences that are more interesting. So you can see in the last 10 seconds we've processed this many events and that kind of thing. So yeah, I'll give you a little demo of that. So I've got a Pixie run, what did I call it? Event, no, I think it was monitor events. So this is just going to run the SK Tango event monitor here, and we pass in all the devices we want to listen to. So I'm listening to our average device we were just looking at, and then there are these two demo devices here that Anton made, yeah, and then this is kind of taking snapshots and outputting snapshots for all the different devices and that we're monitoring right now. And so the first thing we get is just a list of all the new things we saw. So we've seen that the average DS device is publishing all of these things here, and this made all these subscriptions, and we can see that it's already processed 131 events for this CPU percent. And then there's this last server counter, which, so in the event protocol, every event is sent with a counter by the server, and this is the last counter that we received from the server on this particular client. And these two values here, 131, can get out of sync if the device server restarts, then this counter gets reset, but we still process some events. And similarly, if our client restarted or some other client had subscribed already, then maybe we've only seen 60 of these 130 events or something like this. And we can see here that no events have been missed by Tango. So that means we've never seen a skip in that event counter. So every time we've received an event, it's been the event counter we're expecting. And we've had one discarded event, because sometimes ZMQ sends us the same event twice, and so we've got the same event counter that we've just seen, and so we just discard that and we don't call your call back again. So we can see here, all these events have been processed, and if we went and found where we've subscribed to, so this is our averager device, which is the client in this case. If we went and looked at the publisher, we can see there's 131 events have been sent. And these things are all in sync, so that, all these numbers are the same. I need to make the font a bit smaller, don't I, to make this table. Is that still readable? Okay, so I passed it right at the very top of this. I passed the M flag to this script here, wherever it is, which turned on that event system with the performance monitoring. And then what SK Tango Event Monitor does is it does some statistics on all the events that it's seen and just prints you a nice summary of what's going on. So we can see here that in this 10-second period we received only 1 or 2 events. So 3 events in total. So 1 for this particular CPU percent and 1 for this one. And we can see how long it took to process all of those events on average. So around about 600, 700 microseconds. We can see that large latency again. And things like how long were we sleeping between events. So here we were sleeping for on average 5 seconds between events, which means we're mostly not doing anything, which is good. And this is, and I think, so this is a system that's all working, and so the stuff we're looking at now is not particularly interesting. So I have prepared a broken configuration. So if I go back here, can I stop this? Okay, we'll ignore the segfault. You can't ignore it, it's big red there. Okay, so I think if I do pixie run, start averager, and then I type broken at the end, it should start my broken version of this stuff. And the way that this deployment is broken is I'll show you the problem, and we can maybe, if I've got enough time, we can try and work out what the problem is. But if I start Jive, which is hopefully big enough, I can start up our broken averager device. Don't worry about the broken device, that's fine. And we can start our averager device, and we can have a little look. And I'm going to make something interesting happen, I'm going to try and compile CPP Tango on this screen here, and hope to just use a bit of CPU, and we should see eventually our CPU percentage climb. And then I'm going to go and stop CPP Tango. So now I shouldn't be using any CPU, but for some reason I don't seem to be receiving any events here, and this is just stuck at 99%. And if we waited a while, it would eventually go down, but I think I've made it. I wanted to make sure it definitely took too long, so maybe we're not going to wait for it to go back down. And I'll just close this. Oh, did it start going down just then? Okay, good. But what we can do is we can start our event monitor script again. So pixie run monitor events, and this time I'll type broken. And now we can, if we kick off CPP Tango again, maybe we can see what's going on. I don't want to run CPP Tango for too long because it might make Zoom sad. So we'll just run it for a little bit. So while we get some data. Okay, maybe that's enough. And then, so we can sort of see here in this particular snapshot that we've received up to event 24 on our client side, but hopefully on the server side we've sent much more. Yeah, so look here, so this is CPU percent. We've received, we've processed event number 24, but we've already sent number 41 over here, so there's something fishy going on. And if we go and look at this performance data we've got here, we can kind of already see the culprit. But the latency has grown to 36 seconds, which is why it's taking so long for the GUI to update in the end. And we can look here that the problem is our memory percent processing time is on average 1.29 seconds, which is far too long for the number of events we're receiving. And it's maybe a bit of a clue. If we go back up to the top here, we can see that there are 2 callbacks registered. And if we were paying attention before, there was only one on the working system. And the problem, as it turns out, and I'll just jump to the chase so we can have some questions, is that inside, if I start Jive again, inside our broken deployment, there's this rogue device that we ignored earlier. And if we found the source code for this thing, so I can't do that, can I? If we find the source code for this thing, which I think is in, I think I called it just rogue device. We're subscribing, we're using the async submode, so that's fun. But we're in our callback, we're sleeping for 3 seconds. So on average, whenever we get one of these events in our event server, we're taking far too long to process all these events. And I think the important point here is that this device has got absolutely nothing to do with Anton's device. And it's just because we've deployed them all on the same device server. And this thread that services these, that calls these callbacks, is a shared resource. And so you have to be very careful. I mean, I don't think anyone would sleep for 3 seconds in these things, but if you're not paying attention, you can get yourself into a lot of trouble if you don't think about the device server as a whole and just think about your device in isolation. Yeah, I think that's all I've got to say. Any questions?
Okay. Questions? Здесь still processing the callbacks as well.
Thanks, Thomas. So at the moment, this is all, you have to call the command in order to get the stats fundamentally, right? Is there any part of this that you could expose, as an attribute that we can put into the EDA and so on, or is it too heavy to, kind of do that constantly? Whether per attribute or aggregated, or, I'm just wondering if there's some kind of useful proxy of, like, event system health that we could archive.
I worry that it would be too heavy, but we could explore somehow exposing it and somehow... I mean, you could make a Tango device that goes and calls this on other Tango devices. But one thing to remember is every time you call this command, nothing can subscribe to events on your device server. Nothing, we're blocking it while we make this JSON string, which is not cheap, like it's not free to make a JSON string. And so I don't know about archiving it all the time. Maybe, we can look into it. Thanks.
Well, I have one question. How it can be linked to observability and OpenTelemetrics? I mean, it's pushing an event, a transaction that we can observe using observability.
So right now, the OpenTelemetry doesn't support events, which is why I added this, because I needed it now. But I think if OpenTelemetry had supported events, then maybe that would have been a solution, because you could have done all this statistical stuff. That you would have had all of those times, those spans for how long all those different bits took. That would have all been there, but right now we don't have OpenTelemetry doesn't do events, and we don't really have a story about how we're going to do that. So this is just solving my immediate problem, which is I wanted to see what was going on.
Thank you, Thomas. If I understood correctly, this is a feature that can be used only with the device server?
Not in 10.3. In 10.3 now, on API util, there is a command so if I go tango.util. This isn't going to be very interesting yet, instance, and then I can do query event system, I hope. Yeah, so there's nothing going on in this particular Tango instance, so we just get null and null. But if you were running, you could call this in your script, say, to know what events have been done. And I've recently started calling this in the CPP Tango. I've got an MR to start calling this in the CPP Tango tests. So after every test run, we know all the events that were sent or received by the test, which we can maybe things like that would be useful.
Okay, I think it would be useful for Taurus, for example, for the client to get the insight of how is going on the event system. Thank you.
Another question on this side? No? No? No more questions?
Thanks. I just want to understand the rogue device. So the rogue device and the average are running in the same process.
In the same process, yeah.
And when we receive an event, there's a single thread that
Yeah.
services the whole process. So all the devices share that thread, and if one of them blocks on dealing with the callback, it stops the other ones receiving events as
Exactly.
well. Okay.
So the thread is just going, pop an event from ZMQ, go through all the callbacks and call them in order. So if your callback takes 3 seconds, then we're not going to pop anything else from the queue. We're not going to do anything else. We're just going to sit there
And if the rogue device was standalone, a
in a
separate
different
process,
process.
then it would be slow and its 0MQ thread would fill up.
Yeah.
Would that back pressure affect the server? Or?
Oh, good question. I don't think so. I think the way that the ZMQ hub sub is designed is that badly behaving client doesn't affect other. I don't think the server gets back pressure. I think maybe TJ knows.
ZeroMQ has a high watermark for a certain number of events, and as soon as that high watermark is reached, events get dropped on the client side. And it doesn't affect the publisher.
Yeah, so that if you had if you followed the one device per device server paradigm, then you would have one thread to service your callbacks per device server as well. But only when you start bundling them together, you're now sharing that resource.
But you can also set the high watermark. So if your system is somehow set up, if you have enough memory, you can do that, and well,
You're just delaying doom, right? I mean, you start dropping events then 5 minutes later. Make your callback faster.
yeah, that's obviously the best thing. Yeah.
As Thomas said, we can also use buffer instead of callback. So if we are expecting many events, use the buffer. And process it from time to time, yes.
You have exactly the same problem because you will use memory for storing the event data, and it really doesn't matter where you use the memory because, I mean, the high watermark is just like the number of events in the queue, and the event queue you're using, you also have to set the event size. So, yeah, not a big difference.
If I may promote TIs and my work, we have written a document about best practices, exactly targeting that situation. Publishing, subscribing, callbacks, and what to do, how, when.
And where is that document and this very nice tool available?
I think I put the link in my last slide. To that
There's the document.
Maybe.
This is the document that's available. It's not an SK internal thing.
Yeah, it's also in Sam's
We can put
slides.
some links somewhere.
It's in Sam's slides as well.
Okay,
the link.
great. Yeah.
It's not the same link I posted. So
Yeah, you put.
I put another one.
We
so
can find
I will
some.
add
Yeah.
this.
Okay.
So if there are no more questions,
Let's thank all the speakers today Let's thank the chairs of all the sessions. Let's thank the live demo kernel developers who have done a huge amount of work to prepare these sessions. I hope you enjoy. I personally learned a lot of new features that are present now in Tango. And I wish all of you a restful evening and see you tomorrow at 9.
Well, just before leaving, I have some advice for tomorrow. We just received an email from Alba and from the, let's say, from local government. Tomorrow we have both the visit of the Pope to Barcelona and strikes in the highway. So plan your travel tomorrow accordingly, because teachers strikes. Yes. So tomorrow, let's. I mean, if a hotel is near here, you should have no problems to come. If you are coming from Barcelona downtown, plan your travel time ahead, because it will be a trouble morning.